Hey guys, my name is Cameron Hoefer, and today I'm going to be talking to you about mantle flow, plate motions, and slab geometry at north-south dipping subduction zones in the Greater Pacific. Before we dive into the topic, I'd like to say thanks to Dr. Andrew Laskowski. He was the project supervisor, and he provided a lot of valuable guidance and feedback throughout the project. So thanks, Drew. So this whole thing started with a paper by Ficini, Zilio, Doglioni, and Guria, published in 2017. In which they argued that global eastward mantle flow is preferentially steepening and shallowing east-west dipping subduction zones. So I was curious if north-south dipping subduction zones are being affected by mantle flow, since they're significantly less studied. So the way that I went about answering this question was sampling all these at 2-degree intervals, and all these sample sites, the variables of plate motion on either side of the trench, plate stress, mantle flow on either side of the slab, trench strike, slab depth, and slab angle were all looked at. So we've got the Aleutians in Alaska, Java and Sumatra, New Britain, Caribbean, and Mexico and Central America. So the way that mantle flow is measured is using seismic anisotropy. Seismic anisotropy is the polarization of seismic waves with the crystal or lattice preferred orientation of minerals. So in this case, we're looking at the upper mantle because that's where the subducting slabs predominantly are. And the upper mantle is mostly olivine. So most olivine is A, C, and E type in the upper mantle. And what that means is that the fast direction of the olivine lattice aligns with mantle flow. So when you see the seismic wave, you get a nice line that's lining up with mantle flow. However, sometimes you have these B-type olivine fabrics. These exist in high stress, low temperature environments with some water, which inconveniently is subduction zones sometimes. So there's some uncertainty as to how common they are and to what extent they exist within these systems. So that kind of makes it challenging sometimes to interpret if you're looking at parallel flow or trench normal flow. This little figure here is showing trench normal flow and trench parallel flow, and this is toroidal flow, which is flow in response to an obstruction. Here we've got some scatter plots looking for a relationship between the variables in this study. So these upper two are sample sites with parallel flow, and these are sample sites with normal flow. The x-axis in all of these is slab angle. Over here we've got upper plate velocity, and over here we've got upper plate stress. So these three do not have any correlation, but for trench normal flow, we've got a strong correlation between slab angle and upper plate velocity. So you can see as the upper plate increases its velocity, the slab angle also increases. And interestingly, Lallemand, Hoefer, and Bottlier in 2005 found this exact same relationship. They looked at it a little differently. They split the slab up into an upper and lower section, but if you see, you've got the same trend, increasing velocity and increasing slab angle. Down here, we've got some figures I made showing the relationship between these variables of mantle flow, slab geometry, and plate motion. Blue arrows are plate motions, the yellow arrows are mantle flow, and the red lines are 20-kilometer depth contours. So the first thing you'll notice is that the mantle flow is almost always either trench parallel or trench normal. It's very rare that it's oblique. And typically when that does happen, it's because the flow direction is switching. There's not a super strong controlling influence from one of these variables over all the others. But what you will find is most of the time when you have a change in the direction of mantle flow, it's due to some sort of property of the slab. So here you've got a tear. So here the slab is really deep, here it's really shallow, and the mantle is flowing in a toroidal fashion through the tear. Here the mantle is being squeezed by this really sharp curvature of the Banda Trench. And then in the Aleutians in Alaska, you've got this change from a steeper subduction zone to a shallower one, and the mantle is changing directions. All right, guys, thanks for listening.